Okay, so today we're going to be talking about proving limits involving trigonometric functions. So suppose we have a problem like this. Suppose we want to show that the limit as x approaches 0 of sine x is equal to 0. Let's prove this formally using the epsilon delta definition. So before, I guess I better define sine. Okay? If you remember, the way the trig ratios are defined is we start with the unit circle, okay? And let's say we're just looking at the first quadrant. We label x to be this angle over here from the positive x-axis up here. And sine and cosine are defined to be the coordinates of this point on the unit circle. So this is a circle of radius 1. And this point is now defined to be cos x comma sine x. Okay? So all sine x is the height over here that this point is at. This height over here is sine x. And this base over here, this is a right angle triangle, this base over here is cos x. All right? And of course, the hypotenuse of the triangle is 1. Okay? So that's how sine x is defined. Now, we have to remember that x is in radians. It always is in calculus. Okay? X is in radians, and this is a unit circle. So what does that mean? Well, by definition of radians, okay? The arc here, remember the formula, arc equals r theta? Okay? The arc has length x, okay? The angle, x, times the radius 1 equals the length of the arc, x, okay? So again, this is the definition of sine and cosine. It's defined to be that point. And by definition of radians, this length here is x, that arc, okay? So for sine x in radians, what can we conclude from this unit circle? Well, one thing we can conclude is that sine x is always less than or equal to x. It's the little inequality that follows right from the definition, okay? Sine x is less than or equal to x follows from definition. Okay? Now, this inequality holds for all positive x's. You can see as you go around the circle, sine x keeps getting bigger, but so does x. And x is always bigger than sine x because if you look at this, here sine x is just the height of this point, while x is the length of the entire arc. Okay? The arc has to be longer than just the vertical drop distance. Okay? As we go around the circle, both sine x and x increase, but x increases a lot faster. Then sine x starts decreasing again, but x keeps increasing. And as we keep going around the circle, we see that sine x will be bounded. It'll oscillate between -1 and 1, while x will just keep growing and growing. So this inequality is valid everywhere, most useful when x is fairly small. Okay? Now, when we go the other way on the unit circle, if we were to make x negative over here, the inequality still holds, but you'd need absolute values. If you think about it, if you do have another arm over here, sine x is going to be negative, but x is going to be a larger negative. So in fact, a better way to express this would be by putting absolute values on this. So this holds just for positive x's, or x equals 0, but the more general inequality, sine x less than or equal to x, like that in abs values, holds for all real numbers x. So this follows from the definition and holds for all x and r. Okay? And this inequality is going to be important. It's going to play a role in our proof. So let's now get back to what we were doing. Let's prove that the limit as x approaches 0 of sine x equals 0. Okay? We've talked about the definition. Now let's actually do the proof. So if you remember, first you begin with your let statements. So proof. Let epsilon greater than 0 be given. Let delta equal something. And let x satisfying 0 less than x minus the limit, or rather the point we're approaching, 0, less than delta, be given. And what do we want to show? We want to show that sine x minus 0 is less than epsilon. Okay? So, going back to the definition here, using this inequality, we can complete this proof in just a couple of lines. Okay? Sine x minus 0 is just equal to abs of sine x. Maybe I better put that step in. Equal to abs of sine x, which is less than or equal to x by our inequality, which follows from the definitions, which, by the way, is equal to x minus 0. Let's just explicitly put that in, which is less than delta by this statement over here, which we're supposing. And now to complete the proof, all we need to do is set delta equal to epsilon. Done. So let delta equal epsilon, and the proof follows. Cool. Pretty straightforward. Now let's try a slightly harder example. All right, so for example 2, let's prove that the limit as x goes to 0 of cos x is 1. Okay? So I drew a slightly bigger unit circle. All right? We're going to prove this geometrically again. So looking at the unit circle, we're going to figure out what inequality to use that will help us bound cos x minus 1. Okay? So we have our three let statements written, and we want to get a bound on cos x minus 1. Okay? So we have to get a bound on this in terms of x would be nice, because we know something about the size of x. We know that it's less than delta. So let's go over here to our unit circle, and we need to try to bound cos x minus 1 above by something involving x. Check this out. I'm going to draw a line connecting this point and this point. Okay? Not a bad line. Pretty straight. And we make the observation now that the length of this line is less than or equal to the length of the arc, x. Remember, the length of a line between 2 points is always less than or equal to the length of any other curve connecting those 2 points. Okay? So we can now find an expression for the length of this line in terms of sine and cos, and then compare that to x. Okay? So what is the length of that line? Well, this distance here is cos. This distance is sine. This is a unit circle, which means this point over here is at 1. Okay? So this distance over here is 1 minus cos x. And from the Pythagorean theorem, the length of the line is 1 minus cos x squared plus sine x squared under the root. And that's less than or equal to x. So we might as well just ignore the root and say that this is less than or equal to x squared. Okay? Now if we expand this out, what do we get? We get that 1 minus 2 cos x plus cos squared x plus sine squared x is less than or equal to x squared. And of course, cos squared x plus sine squared x equals 1. So we get that 2 minus 2 cos x is less than or equal to x squared, or 1 minus cos x, if we divide through by 2, is less than or equal to x squared over 2. Hey, we got what we were after. Look at that, 1 minus cos x. We have an upper bound on this, and it's in terms of x, times a constant, but that doesn't matter. It's in terms of x, which means we can now use that bound, and then we can use this given information in our proof. So, cos x minus 1 in abs values equals, so we're going to put the abs value in, negative x squared over 2. Okay? Now the abs value takes care of the negative. That doesn't matter. We can just simplify this to be abs x squared over 2. And what do we know about abs x? It's less than delta. So abs x squared is less than delta squared. So this is less than delta squared over 2. And now we're ready to set our expression to epsilon. Okay? We can set this equal to epsilon. Actually, before that, we might as well forget about the 2. Because why carry it with us, right? Delta squared over 2 is just less than delta squared. And now delta squared can be set equal to epsilon, which means which delta do we need? Root epsilon. So we let delta equal root epsilon, And now delta squared will be root epsilon squared, which is epsilon. The proof is complete, and we know that the limit as x approaches 0 of cos x does indeed equal 1. Cool. So there's one little problem with this argument. Well, there's no problem with the argument, but there's a problem with this. How would you think of something like this? Well, let's try proving this in a slightly different way. Okay, so for a slightly different argument, we could just use a trig identity. If you remember, we have a formula for cos x minus 1 coming from the double angle formula for cosine. The double angle formula for cosine, cos 2a is equal to 1 minus 2 sine squared a. This holds for all a and r, and can be rearranged to give cos x minus 1, if we just set a to be x over 2, equal to negative 2 sine squared x over 2. And now we can take this and sub it in here. And it makes a lot of sense to sub into an absolute value an expression involving a single trig ratio rather than a difference of two things. Because if you have a difference in an absolute value, there's not a lot you can do. Whereas if you have a product of things, like a constant times sine, then there's more you can do. You can split the absolute value, and then you can say something about the absolute value of sine. Okay? So here, this happens to be equal to negative 2 sine squared x over 2, which is, of course, equal to 2 abs sine x over 2 all squared. And now we can go back to what we know about abs of sine. Okay? Remember that the absolute value of sine of the input is less than or equal to the abs of the input. So this is actually less than or equal to 2 times, and now just abs of the input. The input here is x over 2. So we take the whole thing and put it in our abs, and then, of course, we don't forget to square it. And now what happens? Well, the abs splits over the top and the bottom. You have 2 squared in the bottom, cancels out with one of these 2's. So what you end up getting here is just abs x squared over 2. So actually, what you end up getting is exactly the same thing as we got here, geometrically. Except this is coming from an identity. So if you can't think of the geometric argument, and who would, to tell you the truth, then you can use an identity, and that can help you with this limit. Okay? The following steps are exactly the same. All right, so let's try another example. This time, x is not going to be approaching 0. X is going to be approaching a different point, pi over 6. Okay? And we're going to prove that the limit as x goes to pi over 6 of sine x equals a half. All right? We got our let statements. Whoopsie. That should be a 6 there. And what we want to do is find an upper bound on sine x minus a half, which involves this term. And if you pause the video and try this yourselves, then you'll quickly run into a roadblock. Okay? It's actually difficult to solve this problem. Ironically, it's a lot easier to generalize the problem and then solve the general version. So here we're looking at a specific point that we're approaching, and we have a specific limit that we want to prove. But if we back up a bit and generalize and prove instead that the limit as x approaches any a value of sine x equals sine a, that actually turns out to be a bit easier. Or it's at least a little bit more transparent what you need to do to begin the problem. Because here, you sort of don't know how to begin. So let's generalize the statement. So I'm going to erase the pi over 6. I'm going to erase the limit here. So x is going to be approaching a. And we're going to prove that the limit as x goes to a of sine x equals sine a. And we're going to do this for all a in the real numbers. Okay? So in other words, we're proving that sine x is continuous on all the real numbers. Now, what needs to be erased? This. We need x minus a over here. And here we need sine x minus sine a in absolute values. Okay? And now, why did I say this is an easier problem? Well, you're trying to bound here a difference of 2 signs. Okay? We actually have an identity for a difference of 2 signs. If you remember, or you can just look this up if you've never seen it. Sine x minus sine a is equal to the following beast. 2 sine x minus a over 2 cos x plus a over 2. Okay? This is just one of the trig identities. Just like there's an expansion formula for sine, there's also a way to write a difference of signs in terms of a product of other trig functions. And as I said before, it's useful to replace a difference of two things in an absolute value with a product of several things in an absolute value. Because you can do more with this. With this, you can't really do anything except perhaps apply triangle inequality, which would be rather useless here. Here, on the other hand, you can split the absolute value over this identity that you get. So let's pull the 2 out first. And then we have abs sine of some stuff, x minus a over 2, times abs cos of more stuff, x plus a over 2. Okay? And now we can say something about each piece, because here we have just an absolute value of a single trig function in each piece here. We know what to do with this, right? Abs of sine of some input is less than or equal to the abs of that input. And that holds for any input at all. X minus a over 2 is a perfectly valid input. It's any real number. So this can be now bounded. This is less than or equal to 2 times abs x minus a over 2. And this is looking good, actually, because look at what we have here. We have our abs x minus a. We know that's less than delta. Okay? What about the cos term? Well, that's easy. Cos is always less than or equal to 1. So we can forget about this term entirely and replace it with 1. And now we have just what we need to finish the proof. The 2's nicely cancel out. This is just equal to x minus a in abs values. And we know that x minus a is less than delta. And delta can now be set equal to epsilon. So delta equals epsilon, and the proof is done. Surprisingly simple. We just proved that sine x is continuous. So now, how would you prove the initial problem that I asked? How would you prove that the limit as x approaches pi over 3, sine of x, sorry, this was pi over 6, equals a half? Well, you could just use this template and substitute in the right a. So I'm not going to write out the let statements again, but if we begin with sine x minus a half, okay, we see that the trick we need in order to simplify this is this identity. So we take 1/2 and write it as sine of something. Sine of what? Well, pi over 6, of course. And now we can apply our identity. So this is abs 2 sine x minus pi over 6 over 2 cos x plus pi over 6 over 2. And of course, the exact same steps now follow. This is less than or equal to 2 abs x minus pi over 6 over 2 times 1, and so on. And we can conclude the proof. Okay? So what this example demonstrates is that sometimes you need to back up a little. The general case might be easier than the special case, because the special case is sort of hidden. If you evaluate sine at pi over 6, you get a half, and then just writing this hides what you need to do. Whereas if you see the sign in there explicitly, you might think, identity. All right? So it's sometimes useful to do the general case first, and then collapse the general case into the specific case that you're looking for. Okay? So this method works for any limit involving a sign. It also works for any limit involving a cosine. We can prove that cos x is continuous on all the real numbers using exactly the same method. It's just the identity here is going to be different. We need an identity for a difference of cosines, and we can find one, and it'll look exactly the same as this, except with a minor modification. Like we'll have two sine terms instead of a sine and a cosine. But otherwise, the proof is exactly the same, and I'll leave it to you as an exercise. All right, so let's take a look at what we've done so far. This is what we've proved. That sine x is continuous on R. We just did that together. What you did as an exercise is prove that cos x is continuous on R. Okay? Really, you didn't even have to do this. We can just recognize that cos x is sine x plus pi over 2. And now knowing that sine x is continuous, we can conclude that cos x is continuous. But we could also prove it separately. Doesn't matter. So those are two pieces of information we know. And now what else do we know? Well, if you think back to video number 5, which involved quotients of functions, if sine x is continuous on R and cos x is continuous on R, we know that tan x is also continuous everywhere on R except where x has a value where cos x would be equal to 0. Okay? So tan x is continuous on its domain. Okay? Everywhere except for at the asymptotes. Okay? And of course, knowing that, we also know that the reciprocals of all three of these are also continuous on their domains. So secant x, cosecant x, and cotangent x are all continuous on their domains. All right? And all of this follows just from this one proof that we did right. Okay? Let's try one more example, this time involving an inverse trig function. For our last example, we're going to prove that arctangent x is continuous on the positive real numbers. Okay? So here we have an inverse trig function, so the proof is going to be slightly different than what we've been doing so far. All right? So first let's formulate what we're trying to prove. We want to show that the limit as x approaches a of arctan x is equal to arctan a. And this is the case for all a inside this interval, 0 to infinity, like that. Okay? So that's what we want to show. So let's do the proof. So first we're going to let a inside this interval be given so that our proof works for all such a. And we're going to let epsilon greater than 0 be given as well. As usual, we're going to let delta equal something, and we're going to let x satisfying 0, well, we don't need this actually, x minus a less than delta be given. Okay? And now we're going to begin with our proof. Okay? So arctan x minus arctan a, we want to mess around with this and then bound it by some term involving that. Okay? And now we're stuck. Or are we? Remember the method from before. We needed to replace a difference of two objects with a single object, or perhaps a product of several. Okay? If you look around, you'll realize that there is actually an identity available for a difference of arctans. Okay? And the identity is as follows. It'll be left to you to find it or prove it or derive it, whatever you want to do. Okay? Arctan x minus arctan a is equal to the following. Arctan x minus a over 1 plus xa. So this identity holds for all x a in the real numbers, except for a few. You can figure out when this goes wrong, right? X times a cannot be negative 1, because then we get division by 0. Okay? But for our purposes, it does hold for all the x's and a's that we care about, because we only care about positive x's and a's. Okay? So this identity does hold for all such x's and a's. And we can replace this with this. Now we're ready to forget about the arctan. Why? Because we have another inequality. Arctan x in absolute values is less than or equal to x. This is another elementary inequality which can be derived right from the definition of arctangent. Okay? In fact, this inequality, x is less than or equal to tan x, can be derived just by looking at the unit circle. Just like we derived the identity sine x is less than or equal to x, we can also do this. Okay? And this one holds for all x and r. Sorry, not for all x and r. For all x that are less than pi over 2, because of course tan x has to be defined. Okay? So from this identity, this one follows, and this one follows by looking at the unit circle. So this one's left to you to figure out. This one follows right from this one here. You just make the right substitution. Okay? So we can replace this entire arctan with just its input in absolute value. So this is less than or equal to x minus a over 1 plus x times a. Okay? There we go. And now what can we do with this? Well, x times a product of these two things, will be positive if they're both positive. Now, a is definitely positive. We want to make sure that x is positive. Okay? Here we sort of already assumed that, but we do need to take this into account because if our delta window is particularly large, then x could be negative, even though it's approaching a, right? So we do need to take this into account. This identity holds for all x and a in the real numbers, they're positive. We can't have x equal to negative 1 over a, for instance. So we have to rule that out explicitly when we pick our delta. Here, we need to, or we'd like to rather, forget about this x times a term. Okay? So we can say that this is equal to abs x minus a over 1 plus x times a. Forget about the absolute value, since we know that the product of these two things is positive. And now, knowing that this is a positive number and we're adding 1 to it, we can forget about this number completely and say that this is now just less than or equal to x minus a over 1. Right? Because we're dividing by something here which is smaller than this, so the outcome is big. Okay? But in order to do all of this, we need to ensure that x and a are both positive. So what does that mean? It means that when we're choosing our delta window, we have to make sure that x is not larger, or rather the delta is not larger than a. Because if a, this is arctan here, if a is over here, and delta is allowed to be larger than a, and our delta window could look like that, and then negative x's could come in. Okay? We don't want that, so we make a restriction here. Delta equals min of a, and then we'll fill in whatever we need to fill in a moment. Okay? Actually, we're ready to do it right now. Because here we have x minus a over 1. We know that that's less than delta, and delta can just be set equal to epsilon. Okay? So delta is equal to the minimum of a and epsilon. Okay? Now, this proof works, but actually there is a little point of subtlety. I didn't consider the case at 0 separately. You might realize that this proof works if you go from left to right, or rather, if we put an a in here in the minimum, okay, a cannot be 0. This excludes the case that a is equal to 0. So actually, I did prove this, but I proved that arctan is continuous only on the strict positive numbers, okay? And a belongs to this open interval, all right? Same thing over here. So we make these little modifications, and this proof ends up working, okay? You can consider now the case of a equals 0 separately and use a right-handed limit, since we do want continuous on r greater than or equal to 0, okay? So I'm not going to write this out. You can write it out as an exercise, but the only modification which would need to be made would be a being set equal to 0 over here, and we're doing a right-handed limit, which would mean that we would drop the absolute value, and we just have x less than delta. okay? And of course, x positive. And then the rest of the argument would be pretty similar, except easier, because this would disappear, that would disappear, okay? And we just have a simple application of this, okay? So write that out for practice. That's it. Thanks for watching.